are mixing problems? Basically, the whole idea behind it is that we can apply mathematics and mathematical computations and such to solve various like physical problems or problems that can occur or can arise in the real world, right? So what we can do, specifically in this course, is we're going to represent physical situations with differential equations, because that's what we're learning about in this class, right? So what mixing problems are, let me write a definition, a little kind of casual definition here. So mixing problems. Okay, so what do? They basically deal with, this is the overall kind of like general definition. Like I said, it's a very casual, flexible definition here. As you can tell by the name, it doesn't sound too technical, right? It's just mixing problems, okay? So we're going to deal with like concentrations of solutions. Solutions meaning like mixtures of water and something, like water and salt usually, or water and sugar or something, in containers, okay? So very basic, and it might seem a little bit trivial, like these kinds of problems, but again, we're just touching on the surface of what they are and how to solve them. And when you apply them to more real-life situations, such as like a container being, I don't know, like the human heart or something like that, and you're talking about fluid and the concentration of that fluid, of that blood, like flowing in and out and stuff, then it becomes a little bit more crucial to deal with, right? So anyways, this is what mixing problems are. And let's get started, and I'll walk you through how to solve a mixing problem. Alrighty, so here's our problem. It says a tank initially holds 100 gallons of pure water. At t equals 0 minutes, so time hasn't started yet, but well, at the beginning of time, a solution containing 2 pounds of salt per gallon starts entering the tank at 3 gallons per minute. That's a rate, right? A volume rate. At the same time, a drain is open to allow 3 gallons of solution to exit per minute. So that's to keep the volume constant at all times, because then we'll have 3 gallons entering per minute and 3 gallons exiting. Okay, how much salt is in the tank after 60 minutes? Alrighty, so I'll list some of the steps that you can take to conquer some of these mixing problems, okay? So for me, step 1 is always to draw a picture, okay? So draw a picture of some sort. And it doesn't have to be fancy. My drawings or sketches are quite rudimentary, I would say. So let's say we have a tank, which are usually depicted as cylinders. Okay, so we have some tank, and let's say we have 100 gallons of pure water in here, okay? So this is 100 gallons. And then it says, well, at t equals 0 minutes up here, a solution starts entering the tank. So that means we're having something being emptied into the tank. So some solutions going in at 3 gallons per minute, okay? And it also says that a drain is open. So let's say the drain comes out of the bottom here, right? And then we have solution exiting as well. Alrighty? So the volume's remaining constant, and then what we're supposed to do is figure out how much salt is in the tank after 60 minutes. So after we draw our picture, what I'm going to do for step 2 while I have this picture here is label what you can. Label, we could say necessary, anything you'll need, or anything you're given. Necessary and or given quantities, okay? Quantities. Alrighty, so what does that mean in this case? Well, we could say, first of all, how are we going to represent the salt content in this entire tank? We could make x of t, some function, okay? Some function depending on time. This is the salt content in tank, okay? Or of tank, we could say. Alrighty? And then we also have, well, at time 0, when time is equal to 0, when t equals 0, we have 0 salt in the tank, right? Because this is pure water at time 0. So this is equal to 0, and x represents how many pounds, right? How many pounds of salt, so the salt content. What else do we have here? Let's say we were to take the first derivative of this function, so x prime of t, and when you take the first derivative, it gives you the rate of change of something, right? So I'll just abbreviate. We have rate of change of what? And that would be rate of change of our original function, whatever that represented. So we have the rate of change of the salt content. Salt content here. Okay, so let's expand off of this on the next slide. So this brings us to step 3, because we labeled what we have. We labeled the salt content. That's what we're most concerned within this problem, and we identified dx dt, or x prime of t, the first derivative, which represented the rate of change of that salt content, okay? So now for step 3, we're going to construct our equation. Construct equation, all right? Okay, so in our case, what we're going to do is take our x prime of t. We're going to say that this is the same thing as dx dt. You could write it either way, okay? That's the same thing. So this is, again, just as a reminder, rate of change of salt content in the tank. So salt content here. Alrighty, so what is the rate of change of our salt content? This simply written in plain English would equal, well, it's the rate of salt going in minus the rate of salt leaving the tank at any given time, right? So this is basically what we have here, and this is called like the balance law or something like that, where you have something, we're just breaking up what's going on physically, okay? So then we have to look at, okay, so how do we represent rate in of salt, that is? So rate in would be equal to, well, we have to say, okay, how much fluid is coming in, like what volume of fluid? And the answer to that would be 3 gallons per 1 minute, right? Remember we were told in the beginning that the solution is entering at 3 gallons per minute, okay? And then we have to say, okay, so how much salt per gallon are we getting? And the given concentration was 2 pounds per 1 gallon. That was the concentration. I'll just write it here. So this is this thing here is the concentration of our solution, of a new solution, okay? Of the new solution being kind of poured into our tank, all right? And then our rate out would be given by, that's a little bit more complicated. So rate out is going to be, well, again, our volume going out is 3 gallons per 1 minute, right? Because we open that drain at the bottom there. And then this part is a little bit trickier, the concentration of our rate out. So this is assuming that like once the new solution is added into our tank, everything is just well mixed and well blended, all right? So that means that, do you remember our x of t? That represents the salt content at any given time of our solution. So what we're going to have to do is say, well, this is going to be our salt content, right? Per how many gallons do we have total in the tank at any given time? And that would be 100, okay? So this is going to be pounds of salt per 1 gallon. Or, well, per 100 gallons, all right? So salt content over total volume there. And this gives us the concentration. Alrighty, so let's continue this on the next slide. So we have our rate in is equal to, and we had 3 gallons per 1 minute times 2 pounds of salt per 1 gallon. So the gallons will cancel out, those units, right? And then we end up getting 6 pounds per minute. And what does this mean? This means that the rate of salt entering the tank at any time is 6 pounds per minute. Okay, 6 pounds of salt enters at any given time. And then our rate out, if we were to simplify that, that would be 3 gallons per 1 minute. And again, I'm just copying this from the last slide. Okay, and then we had x of t, and then this is pounds, per 100 gallons. Okay, so again, our gallons units cancel out, and we get this time 3 over 100 times x of t pounds per minute. All right, so when we put these together and blend them into our differential equation, right, so dx dt is equal to 6 pounds per minute minus 3 over 100 x, and then this is also, these are all pounds per minute, okay? Pounds per minute here. So this thing here is our differential equation that we're going to solve, all right? So in order to solve our problem, because it asks how much salt is in the tank after 60 minutes. So what we need to do is, so now our goal is to find x of t. So that means to solve our differential equation, and then we're going to answer the problem.